means I'm unable to join you in this year row crop agent in service training. Before I get into my presentation, I'll provide some soil fertility resources that are available to agents that they can share with their growers. The first one is utcrops.com. So utcrops.com hosts a host of other websites on insect, on plant pathology, as well as cover crop and other very important crop production information. There's also the UT News, UT Crop News, which provide current information on crop production. To access the soil fertility website, when you click on UT Soil, this would be the home page that it refers you to. So there's a couple of ways to navigate this website. The first one, if you are not very familiar with the website, is to use how to navigate the website. When you click on that, it displays a PDF file that gives you a rundown on how to access the website. The second option is the quick links, and the quick links actually is my preferred option, which I frequently use. When you click on that, it shows this PDF file, and all you have to do is to go through the information and whatever you're looking for. When you click on it, it takes you to that exact page. Say, for instance, you are interested in fertilizer recommendation for cotton. If you click on that cotton or that green square, it will take you to the recommendations for cotton. Another resource that is available for agents is the Soil and Plant Testing Center in Nashville, UT Soil Plant and Pest Testing Center in Nashville. There's a ton of information out there that agents can access. Now, for the outline of my talk, I'll focus on, like I said, 5 very important concepts. We'll talk about nutrients. We'll talk about the various classifications of nutrients. We'll talk about essential nutrients. We'll talk about beneficial nutrients. We'll also look at the nitrogen, phosphorus, potassium nutrient cycles. We'll also talk about soil pH. And with the soil pH, I want you to pay a little bit attention to soil pH this time, because unlike in the past talks or presentation that I give on soil pH, I just focus on the fundamentals. I'll be exploring the relationship between soil pH and very important crop production or management practices. I'll also talk about cation exchange capacity and then run it up with soil organic matter. So soil nutrient. Before I go over my presentation, I want you to spend a few minutes going over each one of these questions. And if you can't answer every single one of them, or you're not very confident about your answers, my goal is that at the end of this talk, you will be able to answer every single one of these questions. So with the nutrient, I'll focus mainly on fundamentals. I'll talk about what are beneficial nutrients, what are essential nutrients. I'll talk about the classifications of essential nutrients and the nutrients that are of importance when it comes to the state of Tennessee for row crop producers. So for a nutrient to be classified as essential, it has to meet 3 very strict criteria. The first is that the plant must be unable to complete its life cycle in the absence of that mineral nutrient. Secondly, the function of that nutrient must not be replaced by another mineral nutrient. And then thirdly, that nutrient must be directly involved in plant metabolism, for example, as a cofactor of an enzyme. So in practical terms, for a nutrient to be essential, the plant cannot complete its cycle in the absence of that nutrient. And then fundamentally, this nutrient should be involved in either functional or structural roles. So plants can take up over 60 different nutrients, but only 17 of these nutrients are referred to as essential, as described in my previous slide based on the three set of criteria. So the 17 nutrients, the 17 essential nutrients are your carbon, hydrogen, oxygen, nitrogen, phosphorus, potassium, calcium, magnesium, sulfur, zinc, iron, copper, manganese, nickel, molybdenum, chloride, and boron. Plants mainly take this nutrient in ion forms or in gaseous forms. So the font size, information on the orange font size, these are the forms in which the plant will take up this nutrient. So for instance, plants, carbon will enter into the plant as carbon dioxide, hydrogen as water. In the case of nitrogen, the plant will take nitrogen either in the form of ammonium or nitrate. These are the two main forms. Plants can take small, minute amount of urea, but it's not very, you can't count on that. So regardless of your nitrogen source that you apply, whether you're using poultry litter or you're using urea, straight out urea, it has to be converted to ammonium and then to nitrate before the plant can have access to it. So mineral nutrient or essential nutrients, can be categorized into two broad groups. We have the non-mineral nutrients and then the mineral nutrients. The non-mineral nutrients, these are derived from water, oxygen, and carbon dioxide. And these are your carbon, your hydrogen, and then your oxygen. Carbon dioxide reacts with water to produce the carbohydrate, which is the energy source for the plants. So these non-mineral nutrients are mainly used in photosynthesis process. On the other hand, the mineral nutrients, these are usually taken out from the soil solutions, and this is just the remaining 14 nutrients. Mineral nutrients can be classified under several groups. I'll focus on just three of these groups that are more important for my presentation. It can be classified based on the amount required or present in the plant tissue. It can be classified based on how it moves within the soil system. It can also be classified based on how it moves within the plant. And there are also biochemical, it can be classified based on the biochemical functions as well. So let's look at the various classes. The first one, based on the amount required or the amount that is present in the plant. There are two broad categories. We have the macronutrients, and these are required or taken up by the plant in larger amounts, meaning that when these nutrients are deficient in the soil, you are likely to see visual symptoms occurring compared to other group of nutrients. So the macronutrients are nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. The other group is the micronutrient, and these are required in smaller quantities, and usually you don't see visual deficiency symptoms occurring. The challenge with micronutrients is that since they are required in very small quantities, they can easily result in plant toxicity, and that is something we have to watch out for. So the macronutrients are iron, chloride, zinc, copper, manganese, molybdenum, boron, and nickel. The second classification would be mobility within the soil system. And this is very important when it comes to nutrient management decisions. Generally, nutrients that are mobile in the soil can have some environmental risk. There's possibility for groundwater contamination as well as surface water contamination. So in terms of mobility, soil nutrient can be classified as mobile and immobile. Again, these are just the mineral nutrients, not the mineral. These are the mineral nutrients. So these are nutrients that move within the soil systems. So we have nitrogen, sulfur, boron, molybdenum, chloride, and manganese. You realize that the ion forms of these nutrients are usually anions, meaning they are negatively charged. And the soil surface, most soil surfaces are also negatively charged. And like poles repel, so the negatively charged soil surface and these anions repel each other. So they are likely in solution. That is why you see this nutrient being mobile in the soil. The only exception here is manganese. With the immobile nutrient, most of them are positively charged. Their ions are positively charged. They are cations, so they are easily held onto the negatively charged soil surface. And this includes potassium, phosphorus, calcium, magnesium, copper, iron, nickel, and zinc. Again, you realize that phosphorus ion or the phosphate is negatively charged, but it's not very mobile in the soil. And the reason is that it forms a lot of complexes with ions and aluminum oxides. To our third and final classification for the mineral essential nutrient. And this form of classification is very, very important because we use it in diagnosing visual nutrient deficiency, because the location of the deficiency in a plant reflects the mobility of that nutrient. So nutrients are either mobile or immobile. With a mobile nutrient, they can be easily redistributed within the plant if there is an interruption of nutrient uptake, meaning that deficiencies typically occurs on the lower or older parts of the plant. Because if there is a deficiency problem, the nutrient on the lower part is taken up to the younger growing parts. And mobile nutrients within the plant include nitrogen, phosphorus, potassium, magnesium, chloride, and molybdenum. For the immobile nutrients, they are not easily redistributed within the plant. So deficiency symptoms will occur on the upper or younger growing part. For example, our calcium and sulfur and almost all the micronutrients except chloride and molybdenum. So in the state of Tennessee, the nutrient of interest for most row crop growers, there's about 7 of them. And this will be your nitrogen for cotton and corn, your potassium and phosphorus for cotton, corn, and soybeans, as well as sulfur. And then for molybdenum, it's very important when you're growing soybeans, because molybdenum is a cofactor of the nitrogenase enzymes, which help in the nitrogen fixation in legumes. Boron is also very important for cotton, and then zinc is also very important for cotton as well as corn. Now, we want to talk about essential versus beneficial nutrients. So we know what essential nutrients are. What are beneficial nutrients? These would also stimulate growth and development, particularly when the plant is undergoing some kind of stress. So they are only essential for certain plant species, to put it that way. And one of the plants that benefits from beneficial nutrient is the sugar beet. Has a lot of benefit to that. Examples of this beneficial nutrient: silicon, sodium, and cobalt. So in the nutshell, essential nutrients, these are universal for all plants, but for beneficial nutrients, they are just for certain plant species. Beneficial nutrients are very important though. So I just want to go over one of the benefits of beneficial nutrient. So plants can be classified into 4 different groups based on their tolerance or their response to sodium. We have our A group, the sugar beets, that are very tolerant to sodium, and we have our D group, or the corn, that are least tolerant to sodium. What happens is that if there is optimal supply of K, the growth we'll see is what is represented in this light green bar. Additional application of potassium, even if the plant takes it up, it's not going to result in additional growth. But what happens is that if we have high sodium present in the soil, the plant is going to take it up. And you realize that group A and B will take up a little bit more of that sodium. And what is likely to happen is that this sodium will result in additional growth, which potassium alone would not be able to provide. So that's the beneficial aspect of this nutrient. Okay, so nutrient cycle. Again, I want you to pause and go over these questions. If you're not able to answer each one of them, or you're not very confident, my hope is that you'll be able to answer each one of these questions at the end of my presentation. So there are three major processes that are involved in nutrient cycling. And as I go through the major three nutrient cycling, my presentation will focus on three of these processes, or focus on these processes, sorry. The first is nutrient addition, and that is simply how these nutrients get into the nutrient cycle, or how it gets into the cycle. So we have examples like chemical weathering. When rocks break down, they release nutrients. We have nitrogen fixation by legumes. We have atmospheric deposition, such as lightning. And we'll also talk about fertilizer application. The second process is transformation. Sometimes these nutrients get into the systems in forms that are not readily available. It might be organic forms or inorganic forms, and they have to be transferred from one form to another. Also, we'll talk about biological uptake and assimilation, as well as interactions and exchange of these nutrients. And then finally, we'll talk about nutrient losses, how these nutrients are lost through the cycle or the system, through processes like leaching, gas emission, fire, and even harvesting crops from the fields. These can all be considered as nutrient loss processes. So we'll start with the nitrogen cycle. But before I get into the cycle, we just want to talk a little bit about nitrogen distribution in the soil. So nitrogen occurs in two major forms in the soil. It could be organic or inorganic, and usually the organic are the ones that are not readily available, they're in forms that are not available, and they constitute a larger portion of the soil nitrogen, about 95%. Only about 0.1 to 0.3% is available in the bioavailable forms or the inorganic forms. So this will be ammonium and nitrate. And these are the forms, again, that plant will take up nitrogen, the main forms that plants take up nitrogen. So most plants can utilize nitrate or ammonium, as well as very small quantities of urea and water-soluble amino acids. So now we can get into the cycle. Again, so the first process we want to look at addition. How is nitrogen added to the system? Again, if you look at this chart here, it looks very detailed and complex, but just follow me and we'll simply digest this cycle and make it so easy and simple. So there are about 5 different ways nitrogen can get into the system. The first one is nitrogen fixation. This is when denitrogen gas in the atmosphere has a very strong bond, so that nitrogen is not available. So you have an association between rhizobium and legume, a symbiotic association where the legume hosts the rhizobium and the rhizobium aids in fixing that nitrogen. Nitrogen can also be obtained through industrial fixation, used through the Haber-Bosch process, and I will explain that in subsequent slides, where denitrogen again is taken from the atmosphere and under high temperature and pressure and catalyst, it's converted to ammonia. So that is one way nitrogen can get into the system. Another means is through lightning. So when lightning strike, they can break up the very strong bond between the dinitrogen ions. And then when it splits it into those 2 nitrogen ions, it reacts with oxygen and we have nitrogen dioxide. And this, when we have water, the nitrogen is converted to nitrates, which can be a way plants have access to that nitrogen. Also, using fertilizers like urea, we can introduce nitrogen into the system. And then finally, using plant and animal residue, they break down to release the nitrogen that is tied to them. So these are the ways nitrogen is added to the system. So I also want to spend a few time to talk about some of the inorganic nitrogen sources that are available. And I'll start with the Haber-Bosch process, which is one of the biggest breakthrough that we have, because up until then, most of the nitrogen sources were from guano sources, and we couldn't have very high concentrations of nitrogen. And the Haber-Bosch process is very simple. All you are doing is that you are introducing hydrogen gas, which is usually obtained from methane, with that NH2 gas and a very high temperature and pressure, and we've got the iron oxide catalyst in there. And what happens is that at the end of the process, you produce ammonia. So that ammonia is sort of the byproduct that is used to produce a lot of nitrogen fertilizers. So if you look at the chart to the right, for instance, the ammonia, if you want to get urea, all you have to do is to add carbon dioxide to generate that urea. And we'll look at a few of the nitrogen sources. So the first nitrogen source, inorganic nitrogen source we'll look at is anhydrous ammonia. And it has the highest nitrogen content of any nitrogen fertilizer. And it's also cheaper per pound of product. But the challenge has to do with the equipment, and you need skilled labor to put it out. Ammonia in this, the ammonia is usually stored under pressure, so it's a liquid. However, as soon as it's released from the tank, the storage tank you see in the picture to the right, it becomes a vapor. So it's very, very important to place the knives way into the soil, or else you're going to lose that. Okay, now we'll talk about the third process. No. Yeah, okay. Okay, so now we'll talk about the third process that is involved in the nitrogen cycle, losses. Again, the chart is a bit complex, but just follow my leading. So the losses are represented in the yellow boxes or circles. So the first one is ammonia volatilization, which I'll talk about. There's leaching, which I'll also talk about. And there is the NOxes, which I'll talk about in subsequent slides. But plant loss, as well as organic matter, these are not very common or not talked about quite often. But these are also losses in terms of the cycle, because the nitrogen is tied up in this plant parts and not available. So the nitrogen loss pathways, there are about four main nitrogen loss pathways. There's ammonia volatilization, there is denitrification, there is leaching, and there is runoff. So ammonia volatilization, when we applied urea-based fertilizers that are not incorporated into the soil and they sit on the soil surface, what happens is that ammonium is converted to, that urea, is converted to ammonium, what we refer to as the hydrolysis process. That ammonium, if there's rainfall, it's incorporated into the soil, so it's very stable and not susceptible to loss. However, if there is no rainfall, that ammonium can easily be converted to ammonia, which escapes to the atmosphere. So ammonia volatilization is simply the conversion of ammonium to ammonia, which escapes to the atmosphere, which results in losses. Denitrification occurs when the ammonium is converted to nitrate. So in the nitrate form, if there's a heavy rainfall that results in some type of ponding or extended saturation beyond 2 days, what would happen is that nitrate is converted to the NOxes, which also escape to the environment. These are potent greenhouse gas sources as well. Again, the third loss is leaching. So what happens is that in very porous or coarse-textured soils, the nitrate can easily leach and can result in groundwater contamination and all of that. So these are the three mains, but the relationship between soil pH and nutrient availability, soil pH and nitrogen fixation, soil pH and nitrogen sources, and a whole of other factors. So pH is the negative log of the hydrogen ion concentration, be it in solution or water or whatever product there is. So in this chart here, again, it looks like a whole lot, but I want you to focus on the right side of the chart. So we'll start with the top information. These are just some of the pH of some common household materials that we use. So the pH of lemon juice is around 2. The pH of bleach is around 12. And then if we move down to the pH scale, so the pH scale ranges from 0 to 14. A pH of 7 is neutral, and a pH of value greater than 7 is alkalinity or alkaline, and a pH of value less than 7 is acidity. And this can be subdivided into various subgroups or groups or classes. Now, where I want to focus a whole lot more is the relationship. So what is the relationship between soil pH and nutrient availability? The availability of nutrients in the soil is greatly affected by soil pH. So if we look at this chart here, on the bottom of the chart is soil pH in increasing value. And the width of the bars that run from east to west, the wider the bar, the more available that nutrient is at that pH. And the narrower the bar, the less available that nutrient is at that pH. Also, the red color indicates that nutrient is less available. So there are a few things we can notice from this chart. The first is that at a pH of 6 and below, micronutrients become more available with the exception of molybdenum. Also, at a pH greater than 6.5, most macronutrients become more available. That means that the optimal pH for nutrient availability for most row crop is around 6.5. If we look at from the chart, it's around 6.5. That's very important because once you start pushing your pHs to 7s, what you can run into is micronutrient deficiency. And to avoid that, you may have to spend extra money to cover some type of micronutrient fertilizer program. But that can be avoided if the pH is around 6.5. The next relationship we want to look at is soil pH and root growth and toxicity. So what happens is that in soil pH of less than 5.5, the concentration of aluminum and manganese increase drastically. And what happens is that this nutrient can retard root growth and can also cause toxicity to the plant. And we'll see a few pictures. So in this picture you see here, the corn plant on the left was pulled from a field that was lined consistently. And the corn plant to the right was pulled from a field that has not been lined for a very long time. And you can see the differences in the root architecture as well as the overall plant health. So that is what high concentration of aluminum can do to the corn plant. The picture you see here is a tobacco plant that is showing manganese toxicity because the pH of that soil is low and there's a lot of manganese available. The plant is taking up that manganese and it's beginning to affect the plant health. So the next relationship is soil pH and yield. Generally, when your soil pH is less than 5.8, it can result in significant yield penalty. Why so? Because we talked about the fact that low soil pH can affect your root. So your root is not able to take up adequate amount of nutrient and moisture that's required for that optimal yield. We want to look at a study that was done out of state, looking at how soil pH can rob lint yield. So on the y-axis is the relative lint yield, and then on the x-axis is the soil pH. And you can see clearly that pH is below 5.8, you can lose somewhere between 5 to 80% of your potential lint yield. The next relationship we want to look at is soil pH and nitrogen loss. So generally, the nitrogen loss pathway that is significantly influenced by soil pH is ammonia volatilization. Generally, ammonia volatilization tends to increase with soil pH, as you can see in this chart here. On the y-axis is the cumulative nitrogen loss over 16 days, And then on the x-axis, we have different soil pH. And as you can see from both nitrogen sources, urea and urea ammonium nitrate, is that as your pH increases, your ammonia volatilization loss also increase. And what is happening in low pH soils, when there's ammonia, the hydrogen ions. So any nitrogen source that is not in the nitrate form would have to be converted first to ammonium and then to nitrate. So the process of converting ammonium to nitrate is what we refer to as nitrification, and it's a two-step process. From this diagram, you can see that the nitrification process generates quite a number of hydrogen ions, which are the source of acidity in the soil. Meaning that any end source, whether it's fertilizer, it's legume that produces ammonium, that if that ammonium is not taken out by plant and it's converted to nitrate, there's a likelihood that it could increase soil acidity. And the acidity varies with different nitrogen sources. So the table you see here is the amount of calcium carbonate or the liming material that is required per pound of different nitrogen sources. And if you can notice, MAP, ammonium sulfate, and DAP, these are the soils that have propensity to form higher acidity in soils. So having said that, the most potent acid-forming nitrogen fertilizers are MAP and ammonium sulfate. But it's also important to keep in mind that DAP can also contribute to soil acidity. The next relationship we want to look at is soil pH and nitrogen fixation. So acidity can significantly limit N fixation. The reason is that the element molybdenum is a cofactor of the nitrogenase enzyme in N-fixing bacteria. If you look at the structure here, you can clearly see molybdenum in there. And because nitrogenase is a key enzyme in fixing N2, when molybdenum is limiting, it can affect its function. And when we go back to this chart here, we look at the lower chart, we realize that at low pH, even at pHs of 7, you start seeing molybdenum deficiency. So in acid soils, molybdenum is deficient. And because it's deficient, the plant is not able to get the optimum nitrogen that it needs. So you can see a decline in overall plant performance. Finally, on soil pH, how do we correct acid soils or low pH soils? Generally, we recommend liming when the soil pH is below 6. And this should be based on a soil test. The reason is that soils have different buffering capacities. And the liming requirement that is given from the lab takes into account all of these different factors, such as soil organic matter content, clay content. This determine how much lime you should put out. Two soils with the same pH may have different buffering capacity, and because of that may require different amount of lime. There are several lime sources, and the common ones are the limestone, whether it's calcitic or dolomitic. There is calcium oxide, calcium hydroxide, as well as other byproducts like wood ash. So how does lime reduce soil acidity? It primarily reduces it by converting some of the hydrogen ions into water. And this is what I mean. So if you look at this diagram here, the soil with a low pH has a lot of hydrogen ions on the soil surface. So when you add your calcium carbonate, what happens is the calcium carbonate dissociates and the carbon displaces the hydrogen ions into solution. And the bicarbonate breaks down to hydroxide and carbon dioxide. And the hydroxide will react with the hydrogen ions to form water. That is how the reaction or the reduction of acidity takes place. Okay. Oh, well. Positively charged, which we refer to as cations. So the cations for the 17 essential nutrients that we talked about, the cations will be ammonium, potassium, calcium, zinc, iron, manganese, nickel, magnesium, and copper. And if these ions are negatively charged, then these are anions, which include nitrate, phosphate, sulfate, and chloride. The second term is soil colloids. So with rocks and big boulders, when we have rainfall as well as the soil formation factors impacting these rocks, it breaks down into very small particles. And with further chemical reactions or changes, these particles form what we call colloid. They are very small, usually less than 0.01 millimeter in diameter. So soil colloids carry negative charges, and these are primarily responsible for the lot of chemical reactions that occur in the soils. So in the same soil, we have cations and we have anions. What happens is that the soil surface or these colloidal surfaces tend to have negative charge. So primarily, they repel anions that are also negatively charged. So like poles repel each other. And anions are mainly in solution except for phosphorus or phosphate that usually forms complexes. On the other side, the cations are easily adsorbed or attracted or held onto the colloidal surface because these are positively charged, and positively charged attracts to negatively charged soil surface. Now let's get to cation exchange capacity. So cation exchange capacity is the amount of cations that can be held by a given weight of soil. So this is where our ion as well as colloids come in. So cation exchange capacity, this reaction occurs on the colloidal surfaces. And depending on whether it's an anion or a cation, it would influence a whole lot. So the cations that we are talking about are held by the soil can be replaced by other cations. So take, for instance, if you look at this picture right here on the left-hand side, potassium in solution, because you have a lot of that potassium in solution, it can easily displace the ammonium. So if you look at this right here, the cation in solution, because you have a lot of it, it can displace ammonium into solution. In the same way, the magnesium in solution can also displace the calcium that is in solution. How does CEC affect plant nutrition? Two ways. It affects how mobile the nutrients are in the soil, and it also affects the plant availability of nutrients. So in this diagram, which is a soil with a high CEC, what you realize is that there are a lot of negatively charges. So cations are held onto the soil surface. There's fewer cations in soil solution compared to a soil that has a very low CEC. And because it has fewer negative charges on the colloids, most of the ions or the cations will be in solution and can easily be lost. That is why in very coarse textured sandy soils, spoon feeding seems to be a better approach to fertilizer management. Because if you put all that fertilizer into the soil, you are going to lose most of those fertilizer with any significant rainfall. In terms of plant nutrition, again, if you have a soil with a high CEC, what happens is that it's able to hold on to nutrient on the exchange site. So when the plant takes up the nutrient, what happens is that nutrient from the exchange site is displaced or exchanged into solution, providing nutrient for the plant. There are several ways to improve cation exchange capacity. Usually, organic matter addition is one of the most effective ways of improving cation exchange capacity. And this can be achieved through conservative tillage practices like no-till. It's been documented that no-till have increased soil organic matter content up to 2% over 30 years. Also, injecting liquid manure, the use of poultry litter can also improve the cation exchange capacity, because the negative charges that we see on the colloidal surfaces can be for clay minerals as well as soil organic matter content. So anything that improves soil organic matter content would also increase cation exchange capacity. Now, finally, we want to talk about soil organic matter. So soil organic matter encompasses all the organic components of the soil. It can be labor or it can be humus. So the labor component is usually the living biomass, the plant litter or residue, as well as the dissolved organic biomolecules, while the humus is the mixture of just the biomolecules. What is soil organic matter plays a lot of important role, and one of them is that it stabilizes soil aggregate and increases water holding capacity. So the picture you see here, the soil in the beaker on the left has very low soil organic matter content compared to the soil on the right with very high soil organic matter content. And you realize that when same amount of water was added, the soil with the low organic matter content literally collapsed. The soil structure just collapsed. But the soil structure of the soil with high organic matter content held to its former structure. That is as a result of the soil organic matter doing that. Also, soil organic matter retains nutrients. Soil organic matter contributes the negative charges that we see on colloidal surface. So the higher your soil organic matter content, you can retain more nutrient and release more nutrient for the plant when needed. And then finally, when organic matter breaks down what we talked about as mineralization earlier, it also supplies nutrient for the plant. Soil organic matter can be increased by a host of different management practices, such as no-till practices, planting cover crop, as well as the use of manure fertilizer application. Thank you. You can send your questions to me via email or text message. Thank you.